and I'll show you on the calculator here. Normal CDF, lower, upper, your mean is 180, and then you can enter it this way. Standard deviation 36 divided by the square root of 84. Now, if I think that was the issue, so you can always kind of pre-calculate that.
Okay.
You just want to make sure you round to sufficient decimal place. Like you don't need to go out to 9, but you ought to go out to like 4 maybe. Okay. So let me do that. I don't have my calculator up. I'll get that up real quick and show you what I mean by that. All right, so you should be seeing that calculator here shortly. Yeah, you are. Okay. So like I said, you can go 36 divided by the square root of 84. Yours might be slightly different depending on, TI 83, 84. So what I meant by that is like go out to 3.9279 maybe. That should be sufficient. Second distribution, normal CDF, very important to use CDF here. Lower is 181. Yours, you're entering. I have to do it old-fashioned way, manual entry here. 180, comma 3.9279, close parentheses, and hope everything worked out. There it is. So let me snip that in case you want to look at that later.
Yeah, that worked perfectly actually.
Okay, so pre-calculate, probably the better strategy for you on problems like this one.
Okay.
All right,
Perfect.
number,
Thank you.
yeah, you're welcome. 18. Okay. All right, for the variance of X, let me write out what the variance of X requires. It requires first well, I'll write it over here. First, you have to find the expected value of X. Okay, and to do that, you have to take X times F of X. So you have to multiply this one times this. Now your calculator can do that in the lists. Do you think you would use lists, or do you think you would just kind of do it, entry by entry here?
Which one's the fastest way?
It's faster to probably enter it, but it's really close. It's like 3 minutes versus 2 minutes. It's still pretty fast.
Maybe the list. We can try the list.
Okay, and I'm not sharing my screen, am I? Okay, I apologize for that. So why do I? All right, let me go to second list. No, you want to go to stat edit. Sorry, stat edit. So in list 1, I'm going to put in the 10, the 20, the 30, and the 40, like that. 10, 20, 30, 40. List 2, 0.2, 0.4, 0.3, 0.1. Very important that you get everything correct. Now, for list 3, I go up to where it says list 3, and I know there's no cursor, but if I were to type something, it's going to do that. You're gonna go second list 1 times second list 2. Okay, and what that will do will multiply list 1 times list 2. Hit enter, you get the results there. Okay. So the expected value of X is the sum of that. Okay, sum of that list. Now those aren't too bad to add up. I'm just going to quit out real quick. If you don't want to add them up because it takes, it's just too difficult. Let me see if there is a sum button. There is not. So if you do one variable stats on list 3,
yeah,
it will give you the sum here. That's the sigma 23.
Oh, okay.
Okay, now that's kind of a lot of work, but you'll see why that it's 2894. That's not too bad to add up. So that is the expected value of X. Let me write that down. You need that number. To find the variance, you need what's called the expected value of x squared. So this is where the list is probably more powerful. You go to list 4 at the top there, your x is in list 1, so you're going to square list 1, and then you're going to multiply it by list 2. Once you hit enter, it goes away. So if you're not sure if you did it right, you have to actually go back and redo it.
Okay.
You need to get the sum of that. So you can either add them up manually or go back to stat, calc, one variable stats, and do it for list 4 this time, second list 4. Again, you're kind of right on the edge of whether you should do it by hand, use lists. I don't know. If it were like 10 entries, lists are way faster. For 4, really close. Okay, so let me jump to the other screen and show you why I was doing all that when I actually thought we were sharing the screen. So the sums, this one was 24. If you do x squared times f of x, the sum is 610. So the variance is the expected value of x squared, 610, minus the expected value of x squared. So 610 minus 24 squared. There's no way for your calculator to do it, as far as I know, to just do it for you.
Okay.
And that ends up being I don't know. Why doesn't that look right? 610 minus
34.
That's not there though.
No.
Jeez. Okay, so I made a mistake somewhere. All right, so that let me go loose real quickly. That's 2, 8, 9, 4. Oh, 23. Sorry, it's 23, not 24. That's what the issue is.
Oh, okay.
So I just fumbled that real bad. That's 81. That is there.
Okay, perfect. That made sense.
All right, 21. So good news is we've kind of we made a good decision here doing lists, because 21, does it ask for variance? Yeah, so we actually do need to do it for 21.
Okay.
It's the exact same approach. So this is going to go, x is going to go in L1, L2 is going to be your P of x. So L3 is going to be x times P of x, or
Okay.
list 1 times list 2. And then list 4 will be x squared times P of x, list 1 squared times list 2. Okay. Do you want me to show you that? Do you think you've got it?
Honestly, I think I've got it since we did the last one.
Okay, it's all here. You do have to get the sums. So let me just color code it. Like whatever you get for right here, it's going to be a minus, I'm sorry, that's backwards. It's going to be b minus a squared. That's your variance.
Okay.
And you get the sums from one variable stats, and then list 3, and you'll have to do it again for list 4.
Okay.
22 looks like
Yeah.
it's next. All right. All right, which of the following is not a characteristic of an experiment where the binomial probability distribution is applicable? So let's talk about which are applicable. Exactly 2 outcomes are possible. That's typically success and failure. So we know that that's not it. The experiment has a sequence of n identical trials. That's also true. The probabilities of the outcomes do not change from one trial to another. That's, in other words, they are independent.
Okay.
And that's also okay. So the answer is this last one. The trials are dependent. They are independent from one another. Think of like flipping a coin. It should be independent, one trial to the next.
Okay.
All right, it's 23. Let me snip this in. All right, larger values of the standard deviation result in a normal curve that is, so here's a normal curve.
Okay.
And all the standard deviation does is it pushes it out. Okay, so there's no skews on standard deviation. It's by definition symmetric. Left looks like the right. Right, so the question is, does it get wider and flatter or narrower and more peaked? Larger is going to get it to be wider. If it said smaller, that would be narrower. So that's why wider and flatter is the correct answer.
Okay. Got it.
All right, the probability that Pete will catch fish when he goes fishing is 0.88. So this is a success or failure. Either catches a fish or he does not. Pete is going to fish 3 days next week. That's your N, that's your sample size. Define the random variable X to be the number of days Pete catches fish. The probability that Pete will catch fish on 1 day or less. The probability that X is less than or equal to 1 is what? So we're going to figure that out here. Success or failure, that's binomial. So we're going to use binom. And then the question is, well, is it CDF or PDF? We talked about yesterday, PDF is when it's an equal, and CDF is when it's a less than or equal to, greater than or equal to. So you got to know how binom CDF works here. So when you put the number in this case 1, no, I think it's NP and then X. I think it's NP and X. The X here, it's by default going to do less than or equal to. So if you wanted to include that number, you have to do less than or equal to. Now, I don't see any, we haven't seen any weird ones yet where it was like greater than this or less than. That would change this. For right now, you can just use this as is. Your N is 3, your P is 0.88, and your X is 1 here. So let's go to the calculator. I believe that's under second distribution, binom CDF, letter A. It's got to be CDF. 3, yours probably says NP and X.
Yeah. I got 0.039. So rounded up to, would I just, yeah, 2.04?
0.38.
Oh.
Oh, no, I'm sorry. No, you're right. You're right. 0.4. Okay. Boy, I would have marked that wrong. Right. And I know this stuff. I'm supposed to be the expert. I'm sitting here marking the wrong one, so that's not good. Yeah. I'd like to discuss more about this, like less than or equal to, greater than or equal to, but it's not applicable unless we see other problems. So, but just know that that's out there. Okay. If maybe it'll come up tonight in your study session or something. All right, so that's 26, 27 as this random sample. Yeah, okay. All right, random sample of 64 SAT scores, that's N. Average of, that's X bar. Standard deviation sigma. We want a 95% confidence interval for the population mean. So that is going to be a Z interval. The reason it's a Z interval is I believe we presume that, well, have you guys done T intervals?
A little bit.
Well, let's try them both. I'm sorry. Yeah, I'm trying to figure out like why it would be one or the other. So do you remember how to get to Z interval? Because I think it'll just want you to put in the X bar, the sigma, the C. and maybe n.
That where I go to stats and then test.
Yes.
Okay, yeah. Oh yeah, I found it.
I'm going to see if I can quickly do the z-test on this other software I use and see if it actually shows up.
Okay, so it'd be 240 standard deviation. X bar is 1400. N is 64. My C level, and then calculate.
All right, so good news is that it is not a t-test, it is a z-interval. So this is,
That's good.
Yeah. Did you get anything that's here?
Sure.
Okay. Any questions on how to do that?
Nope, that was pretty straightforward.
Great. So the key here is that it says confidence interval. That's how you know you're going to use a z interval on that.
Okay.
$28. All right, using an alpha equals 0.04, a confidence interval for a population is determined to be 0.65 to 0.75. For the same data, if alpha is decreased, so that means alpha goes from say 0.04 to 0.01. So when you decrease alpha, the confidence interval gets wider.
Okay.
And if you increase alpha, the confidence interval gets narrower. So this will be like a note card kind of thing. Let me also make the comment here. Sorry, you want the answer here. Looks like it's that one. As sample size increases, the confidence interval gets narrower. Sample size decreases, the confidence interval gets wider. This is the other type of question they often ask. It's not the same as the other one. That's why I'm showing it here.
And then the bottom one was sample size.
So yeah, sorry. So as the sample size increase, oh, it is the same. I guess because we're doing using alpha. That's so the other way this one is mentioned, not to be even more confusing, is when C increases. When C increases, the confidence interval gets wider. When C decreases, the confidence interval gets narrower.
Okay.
C and alpha are related though. Like they'll choose one or the other probably to ask about. Gonna move on to 29.
Yep.
All right. 29 here. Find my cursor. There it is. Okay, the following random sample from a population whose values were normally distributed was collected. The 80% confidence interval for mu is, so I'm fairly certain this is a t interval.
Okay.
Now, I would like to have some more information to know that. Following random samples from, so you're sampling from a population, but what you don't know is you don't know sigma. Okay, but that's sort of implied. Sorry, what were you gonna say?
Oh, sorry. My question was because you said a confidence. When you see confidence, would that be a Z? How do you know it's a T versus Z again?
Yeah, so good question, right? Like, how do you know this? And this one's a little bit unclear to me. Like it's not giving you the information that you normally know because the sample size is so small.
Yeah.
There's sometimes rules like in your classes where they'll say the sample size is less than 30, it's always T. That's maybe, did you see anything like that in the notes?
No.
Okay.
I've seen Z a lot, but I haven't seen much of T.
Okay, let me quickly show you how to do this in the calculator and we'll find out. I'm sorry for being, there's this gray zone in this course where I don't know what you know,
No,
because I'm not, Let me see if you're seeing that. Yeah. So we're going to put our data back into, we're going to put this data into list. So stat, edit. As a reminder, if you need to clear out a list, you go up to the L value, hit clear and enter. You don't have to clear out the list though. You can just overwrite it as well. It's like, depends on what you want to do. So this one's 10, 12, 18. It depends if you're one of those people that you like to get your notifications, looked at, or if you have a million emails that you still got.
Yeah.
Both are fine. Both are fine. So we're looking at list 1, 10, 12, 18, 16. So I'm going to quit out of this stat test. This is going to be a T interval. I'm going to try that first.
T interval, okay.
Yeah, and this time we're using data because we put everything in L1.
Okay.
You have to make sure that lines up because sometimes people change this or you do something in class. We want now an 80% confidence interval.
Okay. Would I leave the frequency the same?
That never changes.
Okay.
That actually might have been how we could have done. Anyway, I'll show you that maybe if we have time at the end. That's how we could have done an earlier problem potentially. So what I'm looking for here is hopefully this one is, yeah.
Oh.
So this looks pretty strongly like letter B.
Yes.
Now I can also quickly do a T interval, I'm sorry, a Z interval, but you'll notice even if you use data, it still wants to know sigma. See how it wants to know sigma?
Oh, yeah.
And we don't know sigma.
Okay.
So that's how you know, plus the small sample size.
Okay, that makes sense. So if I have sigma, I would use Z, and if I
Yes.
don't, the interval.
Yes, very good.
Okay.
All right, looks like 31 is next. I'll grab that and share the other screen. All right, X is normally distributed random variable with a mean of 7 and a standard deviation of 2. The probability that X is between 6.48 and 7.56 is, so this is a normal CDF problem. 6.48, 7.56.
Sorry about that.
No problem. So normal CDF, lower, upper, mean. This time they are giving you standard deviation. There's no sample size. There's no standard error. Go ahead and try that. Should be one of these values.
Okay. I got 0.21282. So B.
Probably B.
Okay.
32. All right, a random sample of 100,000 credit sales in department store an average sale. So that's your X bar. That's your N. From past data is known the standard deviation of the population. Sigma is 20. Determine the standard error. Okay, of the mean. So that's not too bad. The standard error is sigma divided by the square root of N.
Okay.
Two, three, four zeros. You want to try calculating that for us?
Yep. I got 0.0632. So A.
Yes. All right, 34 looks to be next. All right, so it says random samples of size 17, that's N, are taken from population that has 200 elements. So that's big N. Your homework might have had some sort of correction factor problem where you have to take big N and subtract little n, square root of that over n minus 1 maybe. Don't know if that applies here. We'll see in a moment here. So the X bar is 36, standard deviation is 8. The mean and standard deviation of the sampling distribution, okay, R. So the easy part here is that the mean is always the mean. But in your multiple choice here, that doesn't help. That just gets it down to this, okay? Let me pull up your equation sheet. I believe there might have been a correction factor in there. And it also something like if n over big N is smaller than something, to use this correction factor. You have any idea what I'm talking about, or is that all
kind of.
Okay.
No, kind of.
I don't see it on here, but
not really.
All right. So let's take sigma and divide it by the square root of n, which is 8 divided by the square root of 17.
Okay.
That actually looks like it'll be one of these values.
I got 1.940.
Yeah. Okay. Is that clear?
Yep.
Great. All right. Sorry, I gotta go back to find the email again. Here we go. Nope. All right, 35, snipping that in. All right, it is known that the population variance sigma squared is 125. At 95% confidence, what sample size should be taken so that the margin of error does not exceed 3? Okay. So we've got that sample size formula from yesterday. Let me go grab that again. All right, so this problem though is asking for, okay, I'm sorry, it is just asking for this. I thought maybe it was asking for something else. So they're giving you sigma squared, they're giving you c equals 0.95, and they're giving you the error is 3. All right, so notice that you need sigma squared, E, and the z alpha over 2.
Mm-hmm.
The only thing you don't have is the z alpha over 2. So that comes from the c value. Alpha is 1 minus c, which is 1 minus 0.95, divided by 2, divided by 2, divided by 2 becomes 0.025. You're looking for that z value. So that's 0.025. Sorry, that's marked wrong. You're looking for 0.025 in the tail there. So we did I believe we did this using a normal CDF the other day.
Yeah.
So your lower is minus 10 to the 99. No, sorry, no. We used inverse norm. Inverse norm. Because you want the z value. We want to figure out what the z value is. You know the area is 0.025. Your standard deviation, I'm sorry, your mu is 0, your standard deviation is 1. That's what it always is. And then you did like left tail on that. And you should have gotten like minus 1.96.
Yeah. I got negative 1.95, but rounded to 1.97.
Okay. So we're going to put that into formula here, minus 1.96 squared. Now this time they're giving you sigma squared, so you don't have to square it. That the sigma squared is 125. In an earlier problem, we did square it. E though is just E. You have to square that. And do you remember the last thing you do after you calculate this?
No. Round up.
Yes. And I feel like a coach right before you go into the game. It's like, don't forget to round up.
Yeah. I got negative 53.35, so 54.
Yeah, so that negative, you really want to put those parentheses around there or just not include the negative at all.
Okay.
But I think I heard 54, it rounds up to.
Yes.
Okay. All right. 36. Do you hear any music in the background from me?
No.
Okay. Thank you for letting me know. Got some classical playing. I didn't know if it was could be heard. All right. So a professor at a local university noted that the exam grades for students were normally distributed with a mean of 73. It's probably X bar, standard deviation of 11. Students who made 59.99 or lower on the exam failed the course. Wow, that's very negative. What percent of students failed the course? So when it ever asks for a percent is like asking for an area.
Okay.
So you use normal CDF for area. Normal CDF always returns area. So the lower this time is not given. We're trying to find the probability that X is less than 59.99. So whenever you see a less than, that means that the lower is not given. Minus 10 to the 99, 59.99, 73, comma 11, like that. This is going to give you a decimal, so you will have to multiply by 100 to get the value there. So give that a try. I'll check it here on another piece of software I use.
I got 11.85%.
All right, very good. Is it clear? We talked a little bit about this yesterday, like when you use negative 10 to the 99 and when you use the 10 to the 99.
Yes, when the upper and lower is not given, correct?
Exactly. Yeah.
Okay.
Exactly. This one also, sorry, go ahead.
Oh, I was just gonna say I have to actually use the negative button, not the minus, because that's what messed me up last time.
Good. This one did not have a sample size. We didn't have to divide by the square root of anything.
Okay.
Which is what we would have needed to.
And that's I do it outside before putting it in the calculator.
Yes, pre-calculate it, and hopefully, you can get enough decimal place where you don't see anything odd in the answer.
Okay.
Difference wise. Okay. 37.
Yeah.
All right, if Z is a standard normal random variable, what is the value of Z if the area to the right of Z is 0.1213? So they're saying the area here is 0.1213.
Okay.
So when you're given the area, this is when you use inverse norm. For a Z, the mu is always 0 and the sigma is always 1.
And now I'm trying to find the right tail.
Exactly. Yeah. 0.1213, 0, 1, and then you're right.
I got 1.168, so 1.17.
Yes. Okay, now because you're right tail, your answer should be a positive number. If you
Okay.
ended up using left tail because you weren't, you didn't know what the difference was, you might choose the wrong one. So try to make that drawing if you think it'll help.
Okay. And how do you know again which side of the tail it is?
Right here, this
Oh,
word right there. It'll say right, it'll say left. It will tell
okay.
you.
Perfect.
Yeah. 2038 here. Random sample of 25 employees, that's N. Local store has been taken. C equals 0.95. Interval estimate for the mean systolic blood pressure for all employees of the company is from 123 to 139, which the following statements is valid. Okay, so this is more about the language. I want to say sampling procedure repeated many times, 9% sample means. It's either A or C.
I was thinking A.
Yeah, because it's on the population.
Yeah, if I was gonna guess, I would have guessed A.
Okay. I can go look up the wording, but this is probably in one of your slides or on a homework assignment. You would have seen
I'll
that
mark
wording.
it.
Do you want me to spend some time looking at that or move on to 39?
We can move on to 39. If we have time, we can go back.
Okay. We should, I mean, we got 10 more minutes, 11 minutes here. So
Okay.
I doubt these will take 5 minutes each. But I hope not. I was working with a student earlier, problem did take 10 minutes, but this one should not. So manager of a grocery store is taking a random sample, 144 customers. The average length of time it took these customers was 3 minutes. That's X bar. It is known that the standard deviation of the population, so that's, see how it's known population, that's sigma, 95% confidence interval. So is this a Z interval or a T interval?
Is this a Z interval?
Yes, because sigma is known.
Yes.
Okay, so we got 3, 1, and then I think you got to give the sample size and then the C value maybe. I think yours are, it's a list though. I think it's like 3. You just put those in.
Wait. Oh, I see what I did. And then I switch it over to stats, right? When I'm plugging it in instead of data.
Yes, you want to go to stats. Good catch on that because we've been doing some listing earlier.
I got 0.51001 and then 1.49.
Uh-oh. Okay, let me take a look here.
Maybe I plugged it in wrong. I don't know.
3 minutes. Standard deviation of the population is 1 minute. Okay. Yeah, let me go check here. All right, on stat test, Z interval, enter stats. All right, so sigma is, sorry, sigma, I gave it maybe in the wrong number here. Sigma is 1.
Okay.
That's big. X bar is 3. N is 144. Your C level is 0.95.
Okay, yeah, it did change. 2.836 to 3.163.
Great. Let me just snip these in case you want to look at that later.
How did you know sigma was 1.
Yeah, let's go back and look at the problem there again. Let me
Oh, because it's a standard deviation of the population of the. Oh, never mind.
Yes.
I just thought that.
Yeah, now keep in mind, like, I mean, I do this all the time, so I can quickly grab these numbers. Like, you may have to read it more than once. They double up on a number, 144 to be, deceptive.
Yeah.
I label them as I go. That helps as well.
Okay.
Okay, last question here on is your exam likely to be just like this with different numbers, or is it another pool of questions that it could be coming from?
He uses the same exact questions in some of these. He'll put like half of these problems on the exam, or like most of them, and then it'll be a lot of definitions, and then he'll put in like a couple random ones that are like bonus. They're usually said like bonus questions on it.
Okay.
But most of the exam is literally exactly the simulation.
I like that.
Yeah, because I would have not done that well.
Yeah. All right, so here's a couple of formulas for the for this here. So this is binomial distribution, and here's some relevant formulas from your sheet. This is on the first page, top right. So the two key ones that you need to know here is that the expected value of x, or mu, is n times p. And then for this one, they want the variance. The variance of x, you'll see down here, is n times p times 1 minus p.
Okay.
And so that's what we're going to use for this one here. So n times p times 1 minus p, 50 times 0.4 times 1 minus 0.4.
I got 12.
Yes. Okay, so we talked a little bit about maybe going back and looking at 38. I just did a quick search here. I believe it is on the population mean. It's got to contain that wording in there. So I guess I would go with A on this one.
Okay. And then there was another one you were showing. I forgot. It was like
there is another way to do the
oh, it was this one with the big N, I think.
Okay. That correction factor, I mean, I remember I was helping another student and he had like one question on it. It was something like, square root of like n minus n over maybe n minus 1 or something. I don't think that's the case here, though. That's kind of extreme.
Okay. Could you go back to the note card ones? I was kind of confused on that.
These right here?
Yeah. Could you kind of explain that again?
Yeah, so if alpha goes down, what ends up happening is, like, for alpha, let's say alpha is 0.05, which is a 1.96 alpha divided by 2 number, z number. For if it's like 0.01, the alpha becomes like 2.33. And because you're multiplying by the z, this number here, this is your z. That's why it gets wider as the alpha gets smaller.
Okay.
And then the other way is the other way, like that. It comes from that formula. Let me grab it. I should have grabbed that first here. Let me grab it real quick. It's from this right here, where the margin of error on the right here is multiplied. It includes this multiplication by z alpha. So the bigger z becomes, the bigger, the wider the interval is.
Okay.
So the same thing applies here. So when n increases, or this equation still applies. So as n increases, let's say you go from like the square root of 4, which is 2, to the square root of 100, which is 10, you're dividing by a larger number. So when you divide by a larger number, the result gets smaller.
Okay.
You might have seen this in a few of your assignments where it was like, do it for n equals 16, then do it for n equals 100, and you're supposed to notice that they get wider and narrower. You can kind of see it when if you like do a quick z interval where you change n, you make n get bigger, you'll see that it gets, it has this change here.
Okay, that makes sense.
And then C is just another, it's like alpha in the sense that the C, like the bigger your confidence interval is, like you're going from, if you go from like 80% to say 95%, it gets wider because the area that's a wider area under the curve.
Okay. Okay, thank you for explaining that.
Of course, yeah. Is there anything else I can answer real quick here? I mean, I think you're pretty set, but happy to.
Nope, you answered all my questions. Thank you.
Excellent, excellent. All right, let me go ahead and stop the recording here.